So now I want to talk about principal divisors. For some reason, it's not a definition. It should be principal divisors. It's a bit confusing because prime divisors also starts with P. I don't know. But these are just like a little p, and principal divisors are not little p's. They are divisors, or pseudo divisors for now. So if you take any function, I'm going to define a divisor that correspond, or pseudo divisor that correspond to this function, and I'm going to do it like that, notation. And it goes. What I'm trying to do is to encode the zeros and poles of that function, but in just a divisor. Just write all of them. So I'm just going to define it like that. Right, I'm going over all places. And for each place, I kind of encode if it's a 0, and if it is with what multiplicity. If you have 5 here, it means that p is a 0 of multiplicity 5 of x. And if this number is 0, then it's not a 0 and not a pole. Sorry. And if it's negative, say -2, then x has a pole of order 2 at p. That's how you should think of it. It's a way to define a pole. It's not something that you should make sure it coincides with what you know, because that's how we define it. But that's just a way to define, to encode all the information you want about x in terms of zeros and poles. And we don't yet know that this is a divisor, because at this point in time, it could be the case that the function has infinitely many zeros, like sinus function in complex number. There are functions, but they are not going to appear in our setting. But at this point, we don't know that. So it's still in D tilde and not in D. Okay, we'll have to work a little bit. And just for fun, so exercise for us to do now, like 10 seconds exercise. So how can you express the fact that x is in K, well, it's not 0, in terms of principal divisor? So I want here no valuation, namely no prime divisor should have a 0 or a pole, right? Because all the valuations here, I'm pointing at a prime divisor, but I have valuations in mind also, are trivial on K. So this is always what? 0. So you can write like that, right? And this is an if and only if, because a prime divisor of f over k, or evaluation of f over k, it's all the same, has to be non-trivial on f. And non-trivial on f means that if you take something from f, not in k, f not non-trivial on f minus k. If it's non-trivial on f, it means that at least one of them is negative or non-zero. So that's a way of writing in terms of principal divisors this thing. So x is called a principal divisor. I forgot to. I mean, you can cook up all kinds of divisors, but some of them will come from functions. And these are the principal divisors, are those divisors that come from functions. Not all divisors will go to come from in general. Yes. Yeah, exactly. That's what I said. So that direction follows because it's trivial on K, and that direction follows because it's not trivial on F. For example, just so that you'll see it maybe more clearly. So in the rational function field, which is the only thing you know, well, there is this place at infinity, which you didn't talk about at all, right? I guess. But intuitively, the place at infinity is how many zeros, so, okay, we'll see. So let's look at the divisor of x. So this is not a general x, it's this x, right, in the rational function field. So what can you say? Where are the zeros of this x that you know? A 0. And how many zeros does it have there? 1. So I can write 1 times p0, I can just write p0 and same thing. I can just not do that. And what I claim is it has a pole at infinity, because when you plug infinity, it goes to infinity. Another way of looking at it is look at 1 over x. 1 over x has a pole at 0, which kind of means that x has a pole at infinity. And in what multiplicity do you feel that infinity is? 1, right? Because it's like 1 over x has, yeah. So you write it like that. If you're brave, you can write like that. But don't like, yeah. And let's do something more interesting. And the same rational function field. So where are the zeros and poles? By the way, note that we didn't write a lot of things here, and it's an information. It's important information. The fact that you don't have p5 here means that 5 is not a 0 nor a pole of this function. So what about this? Right, you have 3 zeros at p0. Right, so I'm doing a -1 times p1. And then to what extent does this explode at infinity? Twice, right? Because you can remove that. I don't know what you do when you do this, but everyone thinks it's 2, right? It's right. By the way, do you see what happens with these numbers? Like this is 1 minus 1, and this is 3 minus 1 minus 2. The sum is what? 0, and that's going to be a theorem. Every function has the same number of poles as it has zeros. It's going to be a very important theorem. Good. So after the break, we'll start talking about Riemann-Roch spaces of divisors, and then we are going to start to really work. It's going to be interesting. Let's continue. So I want to kind of, because we still don't know that the divisor that we care about are divisor and not pseudo divisors, I will need a kind of a machinery or a way to notationally truncate a divisor. So this is what's happening now. So let's say that you have a subset of the prime divisors, and you take a pseudo divisor. So we write, or we define A sub S. That's still a pseudo divisor, but I'm just zero out everything that's not in S. So this is just a way of taking a prime divisor and a pseudo divisor and truncate it to S, in the sense that I'm putting 0 outside of S and keeping the same information as it was. You see VP of A is the extraction originally. And now I want to give an important definition. So define, so it's like a cool L, I don't know. S is not cool, as usual. So this is going to be essentially a what we're going to call a Riemann-Roch space. So given a divisor and maybe a truncated version of like an important number, some subset of distinguished places, prime divisors, we are going to look at all functions. So that's now functions that correspond to some divisor, such that for every p in S, Vp of x plus Vp of A is at least 0. Okay, so I'll give examples, but let's just read it as it is for a second. Yes. Sorry. No. So, yeah, I mean, okay, so maybe here. Good. So, yeah. Right. So, yeah. So Vp of AS. So the extraction of AS at P is the extraction of A at P if P is in S and 0 otherwise. Right. And so AS as a divisor, is the definition is the sum of those times p. Sorry, good, thanks. Yeah, like A. Exactly. Right. And outside it's just 0. I mean, it's still on all prime divisors, but it's 0 outside. You cannot ignore the other places. You cannot ignore zeros. Like zeros are information. I'm just saying, I mean, it's the same. You still have the formal sum is still on P, not on S only. But outside of S, you just put a 0 in the formal sum. I put a 0 there. No, because the 0 has a meaning, you'll see. It means no zeros and no poles for the function or something. It's 0 is not information. 0. We will see in a second, but I just put zeros there. So it's not like I'm restricting my group to work in the basis which is S. I'm still working in all prime divisors. And actually, you can see it from this definition. This definition cares about zeros. So what's written here? This is a set, a subset of F, okay? And the entry ticket for this set, when is X is in this set. So what do you need? You need it for every prime divisor place in S, but only in S. You don't care about what happens outside. So VP of X, which is, right, this is VP, the old VP. It takes an X, takes a function. Right, so this is either, if it's 5, it means X has 5 zeros at P and so on. So VP of X plus this is the new VP. VP of A is at least 0. So in other words, for X to be here, this number has to be large enough compared to that fixed number, right? Given A, that's a fixed number. So that when you add it with that, you get something non-negative. Or this number has to be at least the minus of that. And this is predetermined. This is part of the definition. For every PNS. So given A and S, these numbers are known. Right? And so for X to be in the set, for every PNS, you have the X has to satisfy some properties. Yes. You don't care about the zero side. Right. To be here, I don't care. Right. But I do care in other. And I'm just defining LA to be LA with P, like S being P, like everything. So it's really just saying like for every P in general, it holds. And let me write it a bit differently. And then maybe, okay. So you can also write it like that. So you can say all X in F, I'll fix that in a second, but let's see if you'll catch me. All X in F such that XS plus AS is at least 0. So you look at this. So to be here, so for X to be here, for every P and S, something has to happen. And the thing that has to happen is that, this thing, which is per P, and instead of kind of listing all of them per S, you can just look at the divisors level, at the divisor level, and ask that. Right, this is a divisor or a pseudo divisor. It's a sum of two pseudo divisors, and this is also a divisor. It is actually a divisor, and saying that is exactly saying, right, that for every P ever, VP of X plus VP of A is at least VP of what's written here, because it's 0, you only care about what's happening in S. Exactly, good. So the only annoying thing is this thing. Because you can't put a principal, you don't have a principal divisor corresponding to 0. No, but here it's fine. That's it. Because VP of 0 is infinity. The VP, you see, VP of a function, VP of 0 is fine, it's infinity. We kind of extended that to infinity. But we never defined the principal divisor of 0. Right. I don't want to put infinity everywhere. I could have done that. Right, but no one does that. I don't know why. Like, different parts in the literature differ, but all of them agree on that one. Yeah, because here it's fine. Right. That's silly. It is silly, but just playing with it is a good. And LA is the same, right? You look at all x in F, that decided, so that x plus A, no S's now, is at least 0, union 0. And the definition, I'll do examples in a second, but let me just give it the name. So Riemann was the advisor, Roch was the student. Riemann proved the first part, Roch the second part, and the inventors the definition under for their name, following the name. If A is a divisor, we don't care about pseudo divisor much. So if A is a divisor, even though this was defined for pseudo divisors, if A is a divisor, then LA is called a Riemann-Roch space. RR from here on. This is where the functions that we are going to evaluate in our code are coming from. We're going to come from Riemann-Roch spaces. We're going to evaluate them at the points of the curve, the evaluations, and the functions are evaluated. The functions that we are going to evaluate are coming from some Riemann-Roch space. So let's do, okay, before doing the example, just to make, let's do the example first. So let's do two examples. I don't know why I decided to put it at the end and only give one example. Let's do it now. So we only kind of understand the rational function field. So let's work there. So in the rational function field, so fix any finite field you want or any field you want. I don't care. K. Think of K as F5. It doesn't really matter for what we're going to do now. So let's look at the Riemann-Roch space of free P0 minus P1. Okay, this is a divisor. I don't know why I wrote the P big, capital, but same P from before. Right, so let's see what does it mean. So this is a divisor. This is actually a divisor now, because it's finitely supported, only finitely many primes appearing there, non-zero coefficients. So let's try to compute L of that. Like figure out what are all functions that satisfy this. And let's break it down so that we can really understand the definition and see. Wow. Oh, it's the other way. Good. It's kind of amazing. It's the same. I thought it's the same example, but it's not. Okay, so let's see. Formally, for a function to be here, and this is where the zeros are important. That's what I meant for the zeros. So you need the following. You need it for every P in P, not only these two. For every P in P, the valuation of X plus the valuation of A, this is A, is at least 0. Right, that's the definition. But obviously there are like two interesting places here and the others. So let's see. So what valuation force do you want to take? 0, right? So if you take P equals 0, so P0, then what is said here is that VP0 of X plus what number? 3, right? VP0 of that, which is this number, is at least 0. So what does it mean? So it means exactly. So this, let me just do this obvious transition. So this means that this function can have poles at 0, but at most 3. Okay, so you can look at 1 over x is there. I mean, I don't know if it's there, but as far as P0 goes, 1 over x is there. Actually, it's not there. There are other places. But okay, so let's look at P. What P? Which should we look now? P1, right? So VP1 of x plus minus 1 is at least 0, right? Because VP1 of A is this number, minus 1. So this means that VP1 of x is at least 1. So this is actually, the first one is a constraint, but you feel like you're given something. You're allowed to have 3 poles. The constraint is at most 3 poles, but you are allowed to have poles at 0. Here, how should you interpret this? At 1, right? You have to have a 0 at 1. I mean, you have to be a multiple of x minus 1. And you would think that's it. But no, at every other place, you are not allowed to have poles. Right? It's like, well, there's nothing else to write, but no. For every p, that's not, and that's what I meant about the zeros. Not p0 and p1, you still need vp of x plus 0, because it doesn't kind of appear there, to be at least 0, which means that p is not a pole of x. So can you give me rational functions that have, well, that's kind of easy to impose, that have at least 1, 0 at 1, and at most 3 poles at 0, and no poles everywhere else. X minus 1. Well, I will excuse you because we didn't talk about the place at infinity. You see, this function has a infinity at infinity. I'm just kidding. But you definitely need an x minus 1 times something. And you have 3 poles. So just to give one example over x. That's a great example. Because this function at infinity it's fine, it goes to 1. So it's not, the evaluation at infinity is actually 1. The infinity of this is 1. It has the required amount of 0, and it doesn't go over the allowed amount of poles. Good, but you can go in, so you need this, and you can go a bit greedier because you're allowed to have 3 poles. Exactly. And then the last one. Right. Yeah, good. So all of these are allowed, I think. I don't see a problem. X minus 1 squared, yeah, good. So all of them are allowed, and you can cook up more, and then you'll figure out that actually it's a vector space. Right, once 1 is allowed, over k, you can use constants. You can add a times this plus b times this plus c times that. That's also fine. We'll talk about that in a second. But, why not? It doesn't add, I mean, the triangle inequality will make sure it's fine. And you can look at other functions that won't seem to be coming from like that, but they actually will. So I think one way of writing it is something like, tell me if I'm wrong, a plus bx plus cx squared. For every a, b, and c. Because this is a linear combination of those. Right, because this is this one, this is that one, and this is that one. The way, yeah. So you see it's kind of a 3-dimensional vector space. Good. Right, so you kind of gave me 3 degrees of freedom, 1 constraint, and other like constraints, but they are kind of even constraints. Don't have a pole, but that's fine. But here you require a 0. Here you are allowed 3 poles. So in a sense, you gave me 2 degrees of freedom, like amortized, and the dimension of the vector space is 3. So it turns out in general that in the rational function field, if you give me k degrees of freedom, you get k plus 1 dimension. In k, constants. It's kind of coming from here because you can look at you can take this to be 1, this to be minus 1, this to be 0.
Yes, but I made it by x minus 1 power of 10.
No, because then you have at infinity a problem. You need to make sure that, so we didn't talk about the place at infinity, but just at least intuitively, you have to have the degree of the numerator to be at most the degree of the denominator. Because if you have x to the 4 here at the numerator, and only x cubed downstairs, it goes to infinity at infinity. Yeah. So there is one more place you haven't talked about, and that's what's stopping you from doing this. We will talk about it today. But that's all you can do, really. Okay, good. Let's do another example. It's a much more interesting example, like not interesting, much more important example, but it actually relies on the place at infinity, so I'm not sure. Let's try to do that still. You understand what infinity means, right? It just means that intuitively, right? Infinity is a pole. If when you plug infinity, you get infinity. So let's look at this. Let's look at this Riemann-Roch space. So I'm taking only p infinity, only 1 point, not like 3p0 minus p1 there, only 1 point, one prime divisor, but times r. And I think of r as a positive number, a 5. So what is this? Let's try to figure out what this means. Am I ruining something for you, Tomer, or it's okay? Yeah. So x is here. So for that to be here, I needed for every prime divisor, for every p, you needed vp of x plus vp of r times p infinity. Let's write it as it, not a, is at least 0. That's what we need. And there are two cases, like p infinity and the others, and p that is not p infinity. So when you take the p infinity, so you know that vp infinity, which you can write v infinity, by the way, because it's like v infinity of x plus what? Plus r, right? Because in this divisor, v infinity of that divisor will give you the r. It will extract r. Has to be at least 0. Or put differently, how should I read this? You're allowed to what? Exactly. We are allowed to have poles, but at most r, I'm kind of thinking of r positive. At most r poles at infinity. Okay. So x is fine, like at least as far as this is concerned. And what about the rest? So you need vp of x plus 0 to be at least 0 for every p that's not p infinity. So what does it mean? No poles elsewhere, like other than infinity. Other than at infinity, right? So what functions do you know that have no poles at all and actually are allowed to have poles at infinity? Polynomials, exactly. Right, polynomials, I mean, a rational function, if you take a rational function, like strict rational function, not a polynomial, it's going to have a pole because why, actually? So if I have a g over h, a rational function, h is not constant, and they're co-prime and so forth. Then what's the problem with h? Right, there is an irreducible polynomial. Maybe h cannot be factored completely, but there is an irreducible factor of h in your field, over your field k, even if it's not completely factored. And that irreducible polynomial corresponds to a place. And at that place, you get a pole. So it's only polynomials. And saying that you're allowed to have at most r, but you're allowed to have r, poles at infinity means that the degree is r, most r. Because x has 1 pole at infinity, x squared has 2 poles at infinity, intuitively. So this is really just, you can write it like that. Polynomials of degree at most r in x. So for example, read Solomon, this is where you take your evaluations, the functions that you are evaluating. Right, so read Solomon is a special case of what we'll call an algebraic geometry code, in which the Riemann-Roch space that we are going to work with is this. Good. Yes, where there is a equality. This is R. It looks like an S. This is like a vertical line meets its three places. Okay, so good. So let's just say what we just, I think with these examples, or maybe I should say one more time. So when you have a divisor, the positives, negatives, and zeros have different kind of meanings. Positive, like a positive coefficient tells you that you are allowed to have poles. Negative, and that's the maximum amount you can have. Negative kind of tells you you are required to have at least one, not like minus 1, 0. And 0 tells you no poles here, but you're not forced to have zeros. And no poles here, but you're not forced to have zeros. Right, so that's how you should think of it. So this means you are allowed to have R poles at infinity, but don't have any other pole. So this is a polynomial of the greatest most. And as we kind of said, this is a vector space. So let's just make sure we understand that. So claim 6, I think I'll leave it as an exercise because it's obvious. So let f over k be a function field. And A is a pseudo-divisor. S is a subset, could be infinite, could be P. Then LAS is a K vector space, which is a subspace of F. Like F is a K vector space also. Subspace of F. Of course, it's a subspace. Right, really, the triangle inequality is what's really important here. Because if X and Y satisfies the requirements, then like VP of X is larger than what it should be, and VP of Y is larger than what it should be. Then VP of X plus Y is larger than what it should be, but the triangle inequality. And also taking the product with a constant, it's fine, because if you take a function in F and you take it multiplied by a scalar in K, then the valuation of a scalar is always 0. So it doesn't change anything. Just do it as an exercise, but it's obvious. No proof. No. And you can also watch the note, look at the notes. So given this, we write dim A for divisor A as the dimension of the Riemann-Roch space as a vector space over K. Okay, so we define dimension of a divisor. And note, for example, this is claim 8, that if S1 is a subset of S2, then what can I say about LAS1 and LAS2?
Has more constraints.
Right. Exactly. Right. So S2, this means when you have an S here, it means that the constraints are coming only from S. And it's the same A. So S2 containing S1 means more constraints here, so potentially less elements, but not more. Right. Okay. Questions so far? So let's prove a little tiny claim that is useful. I mean, what I'm heading for is understanding the relation between the dimension of a divisor and the degree of a divisor. Like before in the example, the degree was how many degrees of freedom do you get to have? That's also a good name for degree, because a good reason for the name degree. Because positives were you are allowed to, and negatives were you are forced to. So they're kind of taking also account the degrees of the prime divisors is how many degrees of freedom do you have, and the dimension is how many things obeying those degrees of freedom. So you want usually the dimension to be large when the degree is large. You want it as you allow more degrees of freedom, the dimension grows. More function satisfies those. In the rational function field, it's going to be the dimension is always one more than the degree. So it's like there are no problems. Like every degree of freedom that you're going to add, you're going to prove it. You have more functions satisfying that. Right? If you increase r to r+1, you're going to get new polynomials that weren't there. And if you are allowed to have, if you will restrict me and require to have a 0 at 1, I'm going to lose 1 degree of freedom. So in the rational function field, it's very simple. But in general function fields, because of the algebraic relation between elements, sometimes you're going to allow more degrees of freedom and not gain new functions. And that's very interesting. The amount to which you fail to get new function is encoded by the genus of the function field that you're going to define. So that's where I'm going. But for now, these are just like small claims that I'm proving. And this is the following claim. So for every pseudo divisor and some subset of the prime divisors and function, non-zero function, what I'm claiming is the following. Oh, yeah, okay. I better explain what I mean by that, but I explain. So just before that, I should have, it's a line before the claim that I omitted, I forgot to look at. So if you take x in f non-zero, let's say, then there is a map from f to f, which is multiplied by x. Right? Any element goes to x times y. Right? It's a linear map over k. Right? I mean, y plus z goes to xy plus xz, which is xy plus z. And it's a linear mapping over k, because if you take a scalar, it doesn't really matter if it's k or not. But if it's in k, if you take a scalar, then a times times xy is like x times ay. Right? X, yeah. It doesn't matter. So it's a linear map over f. It's a k linear map. And that's what I mean here. So here I'm applying so when I write x times a vector space or times a set, I mean just I'm applying this linear map to this set. So I'm taking every element here times x, but you should think of it, I'm taking a subspace of f as a vector space over k, and I'm applying a linear transformation afterwards to it. So I should get another subspace, because that's what happens when you apply a linear transformation to a subspace, and I claim that subspace is nothing more than this. Okay, so this linear transformation takes this Riemann-Roch space to that Riemann-Roch space. It's not really a Riemann-Roch space, because the Riemann-Roch space technically were defined only for divisors, but that's nitpicking. And we are going to call everything Riemann-Roch space. But technically, Riemann-Roch space are only for divisors. Okay, so let's prove that. But do you understand what I'm trying to prove?
The right side is.
Technically, Riemann-Roch space is only for divisors, not for pseudo-divisors. Just technically, just, yeah. No one would remember if I would have said Riemann-Roch space for those. But for some reason, like the name, just so that you know the literature, the name is only for divisors. Not a big deal. But it is, like, other than that, it is a Riemann-Roch space. Like, it is a space that corresponds to some other divisor. And it's a kind of an easy claim, but let's just do it. Because, you know, if you would not do anything, because they're easy, then we do nothing. Okay. So let's just take something on the left-hand side. But there's nothing to it, really. Just do it. So you take an element on the left-hand side and just do equivalent steps and get to the right-hand side. So this thing is as saying that y over x, right? I mean, you can do that. X is non-zero. And then you also omit this symbol of equivalence. So what does this mean, like in terms of divisors, right? It means that for every p in S, Vp of y over x plus Vp of a is non-negative. That's just the definition. The entry ticket for this element to go into this set, subspace. But I kind of want to massage it to look like that. So this thing is Vp of y minus Vp of x. Right, this is how valuation behaves. Vp of AB is Vp of A times plus Vp of B. and 1 over is a minus, so you get this. And now I'm going to do something which is confusing, but it's true. This thing, like in type-wise, this is very interesting, but otherwise I'm going to do this. So why am I so happy? Because you see, this is the old VP, it takes a function, and this is the new VP, it takes a divisor. But this is the principal divisor that's coming from X, and the way we defined it was to put this before P. So the extraction of, so when you extract the coefficient of P in this divisor, by definition, it's this number. So this is why it's a good notation to have VP both for, to use the same VP, not some other U or something. VP both for functions and for divisors. Anyhow, maybe I'm the only one who's happy about this. But then, so this says that for every P and S, VP of Y minus VP of the divisor, the principal divisor of X, plus VP of A is non-negative. By definition, so VP, but what definition, right? So VP of this divisor it's a divisor. So VP of a divisor is give me the coefficient of P in this divisor. This is the extraction. Right. And now you ask, so that's by definition of VP. But now, okay, so what's the definition of this? Because you need to figure out what's the coefficient of P here. So, right, exactly. By definition, VP, the thing that the coefficient of P here is VP of A. Yes.
VP of this is just taking
It back. Yeah, exactly. So it's just a game, a fun game. So right, so before these were friends, these two and this set alone, and now I want to keep this alone. Look at these two, because now this is the same type because these are divisors and this is just a function. So what can you say about this thing now? Exactly. Right, because VP on divisors is additive. Right. And the minus, actually also the minus, so it's another thing. So the minus here goes here like that, like we're minus. Unlike for this, which does nothing. VP of minus the function is the same thing. Right, the function as a polar 0 doesn't matter if it's a negative or not. But VP of a divisor, if you put the minus here, you flip all the coefficients, and so it reflects when you extract them. So it's like a tiny little stuff that you can omit by accident. But anyhow, instead of saying for every PNS this holds, you can just write it like this is equivalent to saying that Y is in the Riemann-Roch space. Right, because that's the definition of this. Because if you open this backwards, so for every P and S, you want VP of Y to be at least VP of this thing. And that's what's plus the VP of this thing to be at least 0, and that's what's written. That's the proof. It's a funny proof. Actually, now we are going to start going a bit deeper. It's not ideal doing it like 15 minutes before the end. What can we do? So my goal at the end of the day is to understand the relation between degree and dimension, and on the way also prove that, for example, principal divisors are actually divisors. Oh, that's a good point. I call them principal divisors, and currently they are pseudo divisors. They don't know that they are finitely supported, so you shouldn't think of it as an adjective. Just the name, principal divisors, and then we'll show that they are actually divisors rather than pseudo divisors, and then it would make sense we actually initially call them like that. Okay? You don't want to call them principal pseudo divisors, and then when you understand that they are divisors, change the name. You don't change the name of the kid because you understand it better, right? You don't, oh, he's funny, so we should call him a different name after he was born, right? So you have a name and then you stick with it. So we chose the right name. Okay. So here is the fourth step. It's like actually the hardest step. So let's say you have a finite set S. You take a finite set of prime divisors, and you take A and B pseudo divisors, A is smaller or equal than B. Right, so you just take a set, a finite set, and you take two pseudo divisors, one is smaller than the other. Then what I'm claiming is that the dimension of this quotient is exactly the difference between the degrees. Right, so you have two pseudo divisors, but then you truncate them to some finite set. And A is smaller or equal than B, in particular also AS is smaller or equal than BS. And so by what we said here, what I said, we know that this is a subspace of that. And so it makes sense to look at the quotient, right, as a K vector space quotient, because this is a subspace of that. And what I'm claiming is that here the situation is amazing. When S is fixed to be any finite set, the dimension of the quotient is exactly what you would expect maybe. It's how many degrees of freedom here you have here compared to how many degrees of freedom you have here. That's a fantastic result. If it was without S, then we would have codes which are impossible to have. Like, you could communicate like in the air, like okay, so that's a bound, a physical bound. Like you can't improve that much. Okay, so only for finite S's and yeah, and you can't use different S's here. That's so I'm not going to finish the proof now, but I'm going to do the steps, the important steps, I think. So we want to prove this thing. And so what I claim is, so first of all, we can assume that A is just AS and B is just BS. I mean, because nothing here nothing in this equation depends on what happens outside of S. Not the dimension of these things and not the degrees. And because the dimension is, I mean, for a function to be here, you need for every P and S, something should happen. You just completely ignore what happens outside of S. So the dimension of this is like, if you put an S here, nothing will happen, same thing. So I'm just not going to put the S here, I'm just going to remove the S to get like, to do it like that. So let's just assume that. And what I'm claiming, and that's the only thing that I will prove, I claim this reduction, I prove this reduction. What I'm claiming that it suffices, I mean, I'll prove the rest next time, but it suffices to consider the case where B is A plus a prime divisor. Yes. Mm-hmm. Yes, exactly. So you look at a vector space in a subspace of it. It gives you another vector. It gives you another vector space. You usually don't write it like in. I mean, you can write it with these dots, but usually I think you write like that. Right? So you give you another vector space over the same field, where you define addition according to cosets. And yeah.
Then this dimension, which is just the vector spaces.
Right. Yeah, it is the dimension of this minus the dimension of that, by the way. It's not like, this is not a, I mean, maybe your question is why I don't write the dimension of this minus the dimension of that, and that's it. But I just want to write like that, but dimension-wise, it is that the dimension of this minus the dimension of that, because that's how, okay, you can prove this, but it's like the first isomorphism theorem or something for vector spaces. Yes, but this is a vector space, I did sensible one. Right. So that actually that's weird, right? So we need to give a meaning for that. But the degree of BS is, it's just the degree of a divisor, which you sum the degrees of the prime divisor that appear in the divisor. Right, by the number. Exactly. So that's a weird number. We need to make sure that we have an algebraic way of thinking about it. Right.
-1, add them up, multiply each
But the
one.
divide exactly with the degree of the prime divisor.
Then 1, there was 1, but in the general case,
Right. Right. In algebraically closed field, it would be just 0 and 1. on like degree is always 1. You don't even see there. But yeah, but generally it could be anything. And what I'm claiming here actually will actually simplify, your worries, is that it suffices to only consider B, which is A plus P. I'll explain why. That's what I'm going to do today. Just explain why this is enough. But the idea is that you can, B is larger than A, and we are within S. So S is finite set. So there is B is A plus some finite number of primes. Maybe one of them appears many times, but finitely many. Because I'm only consider the S parts of them. And S is finite, and B and A are just, what's the difference between them is only supported on S, and there's a finite number, so there is only finitely many P's that you can add to go from A plus B to P. So if I'll prove it to that, what I claim is that I can just continue this process. I'll explain why, but that's what I'm saying. It's enough to do one shot, like one step, not one shot, actually in many shots, one step. And let me explain what I mean more precisely, but just intuitively, that's what's going to happen. So if you remember, this is really the fourth isomorphism theorem, but doesn't really matter. If you have three subspaces, if you have V1, V2, and V3 are three subspaces, this is going to be B, this is going to be A, and this is going to be A plus B, which is in between. Riemann-Roch space. Then I don't know if you remember those, but actually for vector spaces, it's kind of easy. It holds for anything that you want. But the dimension of V3 over V1, you can break it down to the dimension of V3 over V2 plus the dimension of V2 over V1. So because of that, like refining this sentence, it suffices to prove. So it suffices to prove the following. So I'm actually kind of making this more explicit. I want to prove that the dimension of A plus P S over LAS stack P. This is the special case of what I want to prove for the case where B is A plus P. Because then the difference between the degrees is just 1 times the degree of P. Right? And because of this fourth isomorphism theorem, this allows you kind of to break it down like that. Right? You want to understand maybe A plus P1 plus P2 or something, then you can understand how A plus P1 behaves over A, and then A plus P1 plus P2 over A plus P1. You can always add just one prime divisor at a time. And they will just add up to the degree. Where the bracket?
B equals A plus B, then A plus B, right? Because you can sum
this is a divisor, and this is a prime divisor. No. This is not a function. This is a prime divisor. Right. So I'm just increasing by 1 the count here. Right. So if P appears here with some multiplicity, then I just add 1. Yeah. That's what I'm saying. It's not there is no function that corresponds to that. Right. Okay. So do you get that? Maybe I'll do the one last step before, if you don't mind. So it's enough to do that, and then what I'm claiming is that, oh, no, okay, no. Okay, so I thought it's 2 minutes, it's actually like 10. So the next step will be to kind of normalize things and move it so next time I'll show you it's actually enough to set this to be 0 and this to be minus P. That's a special case in which A is minus P. I will show that that's enough. It's enough to prove that. But that uses the approximation theorem that we stated initially. So it tells you that I expected to actually get to this, but I didn't. So next time we are going to even reduce that even further and then prove it. And actually, next lecture is very interesting because we are going to, for sure, define the notion of a genus. And maybe also see the Gopper code. Like prove Riemann's theorem and see Gopper codes. But that's maybe, but definitely prove, define the genus of a function field, which is nice. Okay, see you next week.